joined NC State in 2014 from Shanghai Jiao Tong University, and he did his master's degree and his PhD degree with us at NC State on the project on the data-driven methodology for validation of risk-informed safety margin characterization model. And then he stayed, after his PhD, he stayed as postdoc and leading the implementation of the project that you're hearing today about nearly autonomous management and control system, in short, WAMAC project, funded by APAI project. And so, thank you, Linyu, for doing this today.
Thank you, Dr. Ying, for the introduction. So I guess everyone can see my screen okay, and I will start. Okay. Good afternoon. Thank you for joining my presentation today. And today I'm going to talk about one of our projects. It's called Development of a Nearly Autonomous Control Management and Control System for Advanced Reactors. Okay. So first of all, we will have an overview, and I just want to say emphasize again that you will hear WAMAC a lot in the later slide, and the WAMAC is an abbreviation for Nearly Autonomous Management and Control System. Okay, and so WAMAC is a autonomous control system that transfer from operator-centric plant control to a WAMAC-enabled plant control system. So the whole idea is to replace some works by operator and replace them by WAMAC. We will come back to this picture in later. So this project is fully supported by the APAI maintainer program under the project title Development of a Nearly Autonomous Management and Control System for the Advanced Reactor. And it's conducted by a collaborative effort from several departments, university, companies, and national labs. And in NC State, we're having 3 departments participating in this project. So that's basically all about the project management, and we'll go ahead to the technical part of this project, and we'll begin the technical session with a simple question: why do we need a WAMAC system? So this is a typical classic operator-centric control room, and you can see there are some features for this control room. First, all the control procedures are highly procedurized. They are all written in paper, and it gives all the operating procedures during normal and emergency situations. So the issue of this is all of the procedures are frozen and static. That means you can only conduct the procedure step by step without jumping ahead, without pausing, or without starting from middle. And also, you can only conduct one procedure at a time. And second feature of the operator-centric room is that it relies on operator training and our knowledge. That means during accident or nominal situations, you have to rely on operator perception on the current situation, which means operator have to digest the signals from the reactor and use his knowledge to decide what is the current status of the reactor and make decision on which procedure he should follow. Therefore, so when an operator has limited knowledge or insufficient training, he may conduct wrong control actions, not even mention those scenarios that has never occurred in the operating history for the nuclear reactors. Meanwhile, because it's human operator, so the human judgment can be subjective and can be biased. Another feature of this operator-centric control room is that the control are distributed across multi-person crew. And the issue of such multi-person crew is that it requires high operation and maintenance cost. And when there are pandemic issues like we have right today, it's dangerous to put a lot of person in a single small room. And finally, the last feature of the operator-centric control room is that they use mostly analog instrument control, and that makes the signal processing slow and usually hard to modify. So that's the issue of the operator-centric room, and we also have some new challenges from new design reactors. In recent years, we have been heard a lot of the design of portable and operational flexible and economy viable macro reactors. And those macro reactors are featured to have small sizes with minimized structure system components. And they are also required to have simplified design, operation, and maintenance, and also should have decreased reliance on human actions. So these features of the new macro reactors turns to be not compatible with the classic operator-centric control room. And that gave us a need for autonomous control system which could fulfill part of operator's task. Especially here, I list 3 examples that we expect the autonomous system to fulfill. First is the diagnosis, where the autonomous control system needs to detect and diagnose the fault and infer the complete reactor state at during any situations. Second is the prognosis, is to forecast the short-term transient and consequences of any control action and procedures. And third is the decision-making, where the control system is to rank and recommend the optimal control actions based on the diagnosis and prognosis information. So let's go back to this picture. We'll have better idea. On the left-hand side is classic operator-centric control system. And the operator has to remember all the training material, the risk analysis result, and also the regulatory guide. And so that he can correctly do the diagnosis, prognosis, and decision-making. While with the new NAMAC-enabled operator control architect, the NAMAC will do diagnosis, prognosis, and decision-making. Meanwhile, based on the knowledge that NAMAC learned from those simulations, risk analysis, and regulatory guide. And finally, a recommendation will be provided to operator for final decisions. And that is why we call our system a nearly autonomous control system, because we still have human involved in the control. It's not fully autonomous. So now we have a better idea of why we need a NAMAC system. And then the question is, how should we design and implement such a control system? Because this is a complicated system, and we actually need we need a lot of methodology and technology so that we could deliver the product. So in this technical approach session, I'm going to have 5 sessions, while 2 of them are talking about the methodology and design principles, while the other 3 are talking about the major technologies. So first of all, we will go through the 3-level architect. It represents how NAMAC store, learn, and transfer the raw signal in the system, and to finally make meaningful recommendations. So before we go to the 3-layer architecture, here are some background information. This pyramid is also known as DIKW pyramid, data, information, knowledge, and wisdom pyramid. It's a wisdom hierarchy that represents the structure and functional relationship between data, information, knowledge, and wisdom. And another importance about this pyramid is that it usually represents computationally how decision support system or intelligence system can be implemented. So let's look at the pyramids on the right-hand side. On the bottom level is data, which are usually raw signals and does not have any meanings. However, if we add the meaning to the data, it becomes information that can be useful. And if we can organize the information and in a structured way, they become knowledge. And with the knowledge, if we have further understanding and insight and predictions, that becomes wisdom. So in the NAMAC system, because NAMAC is an intelligent system, it's an autonomous system, it's an intelligent system that makes decisions. So we adopt a very similar structure when we developed our NAMAC system. So on the right-hand side, you can see that it's a 3-layer architecture for NAMAC system. At the bottom level, it's a knowledge base that stores all the data from simulation, operation, documents, regulatory guides, procedure, and so on. And on the second layer is the developmental layer. And the developmental includes the digital twin development and also NAMAC development. So just a brief notation about digital twin. It's a knowledge acquisition system from knowledge base to support different functions. It's similar to the information where we add meanings and store the information in a structured way, so we can use those information for prediction and insights, similar to the DIKW pyramid idea. And the whole point of this developmental layer is to extract the information from the knowledge base, and where some of the knowledge may not be useful, while some of them are extremely meaningful. So we need to extract those knowledge from the knowledge base. After we successfully extract all the knowledge, and we have acceptable digital twins, we will assemble them in the operational workflow, which will convert the raw signal into reasonable recommendations. We will have more explanation for how these are implemented, but the idea is to show you how NAMAC architecture, how NAMAC are designed, and what is the architecture of the NAMAC system. And another major principle for NAMAC design is the development and assessment process. And that is to answer how should we develop NAMAC system in a consistent, transparent, and improvable way. So with this project, we are not claiming to have a perfect autonomous control for a specific reactor during a specific scenario. Our objective instead is to have a smart development assessment process that can produce NAMAC system for various types of reactor based on requirements from all stakeholders. Here, I just give you a simple example on the assembly, the involvement of assembly lines for automobiles. So at the very beginning, the assembly lines are mostly accomplished by human, and as time goes by, we're having those semi-automatic assembly line, and until recent, we're having the smart factory that's all the design and all the development of automobile is fulfilled by computer. And this actually is the involvement of the development assessment process for automobile. And we are trying to adopt some similar thinking in the NAMAC design. At the beginning stage, what we have is so-called classic development assessment process. So as you see from the previous slide, we have three layer architecture. And for each layer, we need to iterate several times until the acceptance criteria are met. And this classical development assessment process is actually inspired by the formal method. And this formal method has been proposed for a very long time. And the objective is to improve the reliability and robustness of computer programming and software with formalized frameworks, workflow, and process. And an example of this formal method-based classic development assessment process is the evaluation model development assessment process by US NRC that aims to develop and validate a computer model used for safety analysis. And the second stage of the NAMAC development assessment process will be an accelerated development assessment process. And this acceleration is achieved with meta-learning techniques. And meta-learning techniques refer to learning-to-learn techniques that can accelerate and optimize the development of database, the machine learning algorithm, artificial intelligence, autonomous control system, and all of the stuff. And these meta-learning techniques are quite a new technology. And there are many high-tech companies using these meta-learning techniques to accelerate and optimize the training of artificial intelligence system. For example, Google has the MorphNet to optimize the neural network architecture. Microsoft has Azure also to optimize the architecture and hyperparameters. And Uber also have this generative networks for optimize their image recognition networks. And that's not the end of the involvement. At last, since we want to involve all stakeholders, we want to have a co-design development assessment process. The co-design refers to the approach that attempts to involve all stakeholders in the design process to ensure the design solution meets all their needs. So the co-design concept is not new. However, it's so difficult and so slow that people cannot feel it is co-design process. However, with the new meta-learning techniques that accelerate our development assessment process, the co-design development assessment process becomes possible. And this is actually the WAMAC involving process, involving paths, especially for the development assessment, in the development assessment process point of view. So that's all about the fundamental methodology. However, we cannot deliver a WAMAC system with just methodologies. We need technologies to implement our goals. And in WAMAC, we have three major technologies. First of all is the operational workflow. And that represents the process that WAMAC transfer raw signals from the reactor to a reasonable recommendation. So WAMAC operational workflow can be summarized as a structured argument that is supported by evidence from different components. And the goal is to justify that a system is acceptably safe for a specific application in a specific operating environment. So if you look at the picture on the right-hand side, first of all, WAMAC is getting raw signals from the plant. And then the signal first goes to the diagnosis system to correctly infer the reactor current states and the potential faults in the reactor. And then those states will go to the prognosis system to predict the short-term transient and the consequences of control actions. Then those predictions together with the diagnosis information will go to the evaluation block, where WAMAC will find the optimum control strategy that with the most preferred consequences. And that preference is stored in a so-called preference structure. For example, it assigns weights between safety and performance of the reactor. That basically represent our preference in maintaining reactor safety or keep the reactor operating. And after the evaluation model finds the optimal strategy, that will feed to operator, who will decide whether to take that recommendation and inject it to the plant, or reject the recommendation and take its own action. So that is a brief discussion, brief explanation about operational workflow. When we talk about operational workflow, we notice that we have the diagnosis to infer the plant state. We also have prognosis to predict the transient of the states. Therefore, we need another technology to correctly do the diagnosis and the prognosis. And that is why we have the digital twin technology. Basically, it tells it's the technology that that answers how WAMAC understands reactor states, find the available control action, predict the transients, and to find the optimum control strategies. So digital twin technology is a way to construct a digital replica or twin for the real reactor, transient, or physical system. So from function perspective, it is equivalent to modeling and simulation like we talk every day, because it stores prototypical conditions, physics, and closures, and the whole objective is to make inference and prediction for real system. However, the difference between digital twin and modeling and simulation is that digital twin are more tightly coupled with the operation rather than to inform the design. When we say tightly coupled, it means digital twin needs to read real-time information from the operating environment, and also it needs to interact with the user in the real operation for any specific objectives. And on the right-hand side, this picture shows the general definition for digital twins. And that usually comes from three aspects. Model aspect, it can be a data-driven model, mechanistic model, or reasoning-based model. Then second is interface. It represents the application program interface, input and output, and also user interface. And the third is the function, which tells the objective of digital twin, use case of digital twin, and the type of the output for this digital twin. And that is the brief explanation for digital twin. And to implement those digital twin, we noticed that we can use mechanistic model, data-driven model, reasoning-based model. In WAMAC process, we are using machine learning algorithms to implement the digital twins. And in this session, you will hear multiple machine learning algorithms that we have been trying to implement and trying to incorporate them into WAMAC system. And that is what makes WAMAC capable. First of all, the first advanced algorithm is artificial neural nets, and I'm sure most people is quite familiar with this approach. It's one of the most popular data-driven method, and it's also used as the major technology in WAMAC project for constructing a digital twin and finally contribute to the WAMAC system. And there are a few major components of the artificial neural networks. First is the neurons. It is the basic elements that receive inputs, combine input with their internal state and produce the outputs. Second important component is the connections and the weights. That represents the ways ways to connect the output from one neuron to the input of another neuron. An example of connection is, for example, the feed-forward networks, recurrent network, or convolutional neural networks. In WAMAC's project, we're exploring two different connections. First one is the feed-forward neural networks. Feed-forward, as the name suggests, information flows only in one direction. Because of the straightforward structure, it is usually the most feasible neural network to develop. However, this neural network are usually memorialized. That means that each input and output pairs are assumed to be independent. But because with the feed-forward network, it is known to be capable of capturing complex and nonlinear correlations between the input and outputs. The second type of connection neural network is the recurrent networks. As the name suggests, that is different from the feed-forward networks. There are information transferring in both directions, and sometimes there's a loop from one neuron to the previous neuron. So with this unique connection, recurrent networks are designed to handle sequence like time sequence, image sequence, or word sequence. Actually, recurrent neural networks are very popular in natural language processing. In WAMAC context, we found out that recurrent networks are very suitable for forecasting and prognosing functions. And third important component for artificial neural net is the hyperparameters. And those hyperparameters usually refer to the constant parameters that are set before the learning process. For example, the learning rate, number of layers, number of neurons, maximum epoch, validation patience, and so on. We found out those hyperparameters are very important in the training of artificial neural nets. In addition to make a structured argument with operational workflow, we can also find the optimal control action by having a machine learning agent who interact with the environment and receive the signals from the environment and gradually induce the optimum policy that has the maximum rewards. So reinforcement learning is a completely black box approach for control system. And as a member of this team, as a member of this project, we have a team in computer science department at NC State that is trying to develop and deploy such reinforcement learning techniques into WAMAC. However, as Judy and Pearl who is the winner of the Turing Prize, he suggests that the observed correlation by data-driven method does not necessarily imply causation. However, the causality tends to be more robust in prediction. What does it mean? Here, I just make two simple examples. For example, if we are having a data-driven model that's aimed to predict variable z based on selected set of input variables, if we're adding additional variable, that can be risky because that can pollute the model with noises and biases. For example, if we have a system where x induce y and y induce z, and our goal is to predict z, if we introduce y as additional variable, and if the y are perfectly measured and the data are sufficient, then our machine learning model performance will not be largely affected by introducing y. However, if our y are poorly measured and contains a lot of noise and biases, that will greatly deteriorate our digital data-driven model performance. However, if we're not adding certain variable, that can also be risky because of the spurious correlation and confoundings. For example, if we have y that can induce both x and y, and our goal again is to get z based on the input, if we're not including y, we may have a spurious correlation between z and y. That can be confusing because that causality does not actually exist. It's not a strong causality. Therefore, the data-driven model cannot be solely used without a method that performing reasoning and represent our human knowledge in causalities. So another member in this project, we have a team at Computer Science Department, New Mexico State University, that is leading the development and deployment of answer set programming into NAMAC. And this answer set programming is a form of declarative programming oriented. It's a reasoning-based artificial intelligence engine. So that's pretty much all the technologies and the methodology that we use in this project. Next, we're going to talk more about case study. That is, what's the current progress, how we use those technology to deliver a product. And the case study is composed by 4 sessions. First of all, we will demonstrate how knowledge bases are constructed. Because our NAMAC system is designed for advanced reactors, and there is no operating advanced reactor in current in the whole world. So to make a proof of concept for NAMAC, we select the EBR2 as the prototype for small modular reactor with liquid metal coolant and fast neutrons. This is just one prototype for us to demonstrate the concept. And here it just shows a brief history of EBR2 reactors. It is completed in 1960s, and they commissioned in 1994. Again, since the EBR2 has decommissioned, we have to use Planck simulator to represent the reactor. And in this NAMAC project, we use a Gaussian model for EBR2 reactors. And on the left-hand side, you can see the nodal representation of EBR2 primary site in Gaussian. And on the right-hand side, you can see a general view of the EBR2 reactors. There are 2 primary pumps right next to the reactor vessel. And there is also an auxiliary electric magnetic pump connected to the Z pipe. And the Z pipe is directly connected to the reactor vessel. And there's also this intermediate heat exchanger that connects the primary side to the secondary side. During the operation of EBR2 since 1963, there has been 1 major and 3 minor binding for the primary sodium pump. At April 23rd and August 18th, 1963, both primary pump 1 and primary pump 2 have severe galling for the lubricants seal and the pump shaft. In this picture, you can see the galling on the shaft very clearly. Then on July 12, 17th, 1965, and also May 18, 1970s, we have the EBR2 have minor binding after long shutdown period due to the accumulation of sodium oxide in the clearance. In addition, there are 2 complete loss of flow accident tests, which is known as SHIRT 17 and SHIRT 45. Both cases, we have 2 primary pump shut down. So in a word, we found out that loss of flow accident, especially the partial loss of flow accident that is due to single pump malfunctions, can be treated as one of the dominant initiating events for the EBR2 reactors. And this will be our focus in NAMAC project, and this is also how we design a case study and make our proof of concepts. Before we go to the case study, we first need to represent the accident scenario by a mathematical equation so that we could do simulations. And in this case study, we have a linear equation for the malfunction of primary pump number 1. That means starting from accident time, the primary pump rotational speeds start to ramping down to a fraction of the nominal speed. And this ramping down is going to last for capital T1 seconds. And on the right-hand side, you can see a picture with 3 samples of N speeds for the malfunction pumps. Similarly, because after we have the malfunction, we need to recover from the accident, from the scenario. We apply a similar equation to the recovering control actions. That is where we're starting from a trip time. We are ramping up pump number 2 rotational speed to a fraction of nominal speed. And again, this ramping up is going to last for T2 seconds. And on the right-hand side of the picture, you can see we have sampled 32 samples of the N speed and also 32 samples of the trip time. That represent different, in total, 1,024 different combination of control actions to deal with the accident scenario. To generate knowledge, because our knowledge base contains simulation database, and we need a faster way to generate the database. So that's why we couple the Gaussian simulator with a Raven interface, where Raven will automatically sample all the control and accident scenario and stores the simulation data in the CSV or HDF5 data repository. That's basically all about the knowledge-based construction. Then we will talk about how we make a NAMAC that is able to convert the raw signal into a reasonable recommendations. So this picture shows how NAMAC is operating with the plant simulator. At time T0, we're having a steady state calculation that is loaded by the SDM file. SDM file is the Gaussian file that stores the steady state calculation and for continue the simulation. Then at the accident time, T accident, we start to inject our pump malfunction by ramping down the pump to 50% in 50 seconds. And after this accident injection time, NAMAC start to collect information then at the recommendation time, the NAMAC will based on the information that is collected between the accident time and recommendation time, NAMAC will make a recommendation. And there are 2 types of recommendation. The first type of recommendation is to continue the operation, but ramping up another available pump to an omega-2 end speed starting at the trip time. Or we could also recommend to scram the reactor if the situation is too severe. And after this recommendation, the NAMAC system will continue monitoring the reactor state by checking the discrepancy between the NAMAC prediction and the measurements. If the discrepancy is exceeding the limit, then we will send a scram signal. Otherwise, we will continue the operation without doing anything. Then the question will be how NAMAC transfer the information to a recommendation. So this is a more detailed workflow that represent the information flow inside NAMAC. So first of all, the NAMAC is going to collect the sensor signal from the plant simulator, and those signals will first go into diagnosis system for inferring the unobservable safety significant factor, and that is to infer the complete status of the reactor. And then that complete information will go to the strategy inventory to find out all possible and available control actions during this scenario. Meanwhile, this complete reactor information will go to prognosis for predicting the reactor states for all options of control actions that is gathered from the strategy inventory. Then all those predictions will feed into strategy assessment, where the strategy assessment will decide which control action and which consequences are more preferred. And that preference is stored in this preference structure, represents the stakeholder decision makers' willingness to accept risk or to accept the performance. After the strategy assessment, make a recommendation that they will feed into the instrument control of the plant simulator. And all these things is happen at the recommendation time. After this time, NAMAC will continue monitoring the reactor states at different time checkpoints, T1 and T2. So basically, this discrepancy checker is comparing the observable safety significant factor from the diagnosis at this checkpoint and compare that with NAMAC predictions. If the discrepancy between those are too large, we will send a scram signal to the instrument control. Otherwise, we will continue the monitoring. So that's all about NAMAC operation. Then we're going to talk about how we implement those diagnosis, prognosis, strategy assessment, strategy inventory in NAMAC system. First of all, it's a diagnosis system. Diagnosis system aims to infer the unobservable safety significant factor, which includes the field temperature or the cladding temperature. And that inference is based on the sensor signal from the plant simulator. A diagnosis model can be a mechanistic model like what we have in common filtering, which is one of the classic approach. The diagnosis model can also be data-driven surrogate. It can be implemented with artificial neural nets. In current study, we're exploring the capability of data-driven surrogates by feed-forward networks and recurrent networks. The reason is that we found data-driven model is more friendly to big size of operational data, and it's also easy to implement. And also data-driven model have flexible form and aware source of uncertainties. And also the learning and training algorithms for the data-driven method are transparent and mathematically defendable. But for the mechanistic model, this learning and training process is usually stored in our brain, which is usually implicit. So here is how we train the neural networks with MATLAB, and it shows that on the right hand side you can see that the prediction and the observation, the real value, they fall onto a 45-degree line. So that means the neural network has a very good prediction capability in predicting the safety significant factor, and same thing for the recurrent networks. And then it's the strategy inventory. The strategy inventory aims to identify all the available control actions based on the current reactor states from the diagnosis, and also based on the safety and component limits. A strategy inventory model can be a random search method, which is one of the example is a grid-based method, or it can be a model-based search algorithm like Bayesian optimization. It can also be a reward-based search like the reinforcement learning. In current study, we're exploring the capability of grid-based method. where we are sampling the rotational speed of primary sodium pump from the nominal speeds to 1.5 times nominal speed. And this 1.5 times nominal speed is assumed to be the component limit for the primary sodium pump. Meanwhile, we were sampling the trip temperature from the current diagnosed temperature to 700 Celsius, and this 700 Celsius is assumed to be the material limit for the reactor core. Then is the prognosis. The prognosis aims to predict the future transient of reactor state for all available control actions from the strategy inventory. So a prognosis model can be a numerical simulation tool, like modeling and simulation, a physical model or numerical solver. It can also be a data-driven surrogate, like we can also do prognosis with artificial neural nets. In current study, we're again exploring the capability of data-driven surrogates by feed-forward and recurrent networks. The reason is we want our predictive simulation to start from any point in the transient. And this is for mechanistic model, we have to start from the initial condition. But for data-driven model, we can actually start from any point. Meanwhile, because the digital twin, we are using digital twin for real-time operations. So we need this prognosis model to have acceptable accuracy and also the fast computational speed. So data-driven model, when they are used in the training domain, they are having the acceptable accuracy and also very fast computational speed. That's why, with those two reasons, that's why we are choosing the data-driven surrogates. And here it just shows how our prognosis model behaves. The first picture, both the prediction and the real value falls onto a 45-degree line, which means the very good predictability for our prognosis model. This is for the feed-forward network, and this is for the recurrent networks. Then is the strategy assessment. The strategy assessment aims to rank strategies and make recommendations on the control actions according to the preference structure constraints. So a strategy assessment model can be a limit surface model, or it can be a utility model. Just for your reference, limit surface represents the boundary of input space between two simulated outcomes. For example, the failure or success, positive value or negative value. Those between the two states, that's the limit surface. In current study, we are exploring the capability of limit surface model by searching for the control action that result in maximum safety margin or utility. And this safety margin is defined based on the temperature constraints and the fuel cylinder temperature. The temperature constraints are made with assumed material limits, while the maximum temperature are predicted by the prognosis model. And by subtract the maximum temperature from the temperature constraints, we can have the safety margin. And in here, you can see the different plot of safety region, where you see the boundary of each shaded area. That is the safety limit surface. And here, different color represents the safety margin with different constraints, different material limits. Also, since we are having a preference structure, in this case, we're having a very simple preference structure that we use to rank the consequences of each available control strategies. So the simple structure is we prefer to have more safety margins. So if we talk about if this preference structure is applied to the time of actual injection, we are meant to have earlier injections. And when it comes to the end speed of pump number 2, we are meant to have a higher speed, as much high speed as possible. So the reasonable recommendation when the loss of flow accident is happening will be to ramp up pump number 2 to its maximum as soon as possible. However, due to the digital twin error and due to some WAMAC system error, we could have some confusions. And here we have two possible confusion conditions. First is the false positive rate. That represents the situation where NAMAC think it is safe, but the plan simulator, the consequence of plan simulator tell it is not safe. And also the false negative, where NAMAC think the situation is unsafe, but the consequence of plan simulator turns to be safe. Those are the two confusions that we possibly have due to the digital twin error and NAMAC error. So here it's just show how the NAMAC performs with all the digital twin implemented, and to test the scalability of our NAMAC system on different computer platform, we have implemented NAMAC system on both MATLAB and Python platform, and we found out a consistent performance from from different platform. That means our system has a good software scalability with respect to computer platforms. And another thing is because we have an operational workflow that connects digital twin, from one digital twin to another. That means the error of digital twin may accumulate as the information propagates through the operational workflow. So in this case, the error accumulation starts from the diagnosis and propagate all the way through the assessment. And at last, we're finding 1.78 false positive rate and 1.68 false positive for Python and 1.78 for MATLAB. Both of the false positive rate are quite small and acceptable. And there's no false negative rates because false negative has fatal consequences, and we have 0 false negative rate, which means the NAMAC performance is quite acceptable, quite good. Also, although we have made a NAMAC system and it has shown very good capability in the training domain, we still want to test the scalability of our system, especially when it is applied outside the training domain. We want to see where is the limit of NAMAC capability, where is the limit of NAMAC system. So to do that, we have implemented multiple digital twin for diagnosis. That includes 49 recurrent networks and around 40 feed-forward networks. And all of them have acceptable errors, but difference is they are trained with different samples from epistemic range of each source of uncertainties. And we measure the strength of correlation between the digital twin error and each source of uncertainties with Pearson correlation coefficient. And a summary of finding is that the digital twin errors are largely affected by the overlaps region between the training and application domain, especially for those in accident scenario, control precision scenario, and the sensor noise. We also found that digital twin error by recurrent networks tends to be more smoother and more stable than digital twin for diagnosis. Not digital twin for diagnosis that is implemented by feed-forward networks, because feed-forward networks are memoryless, while the recurrent networks are much suitable, can remember the sequence. That is why the prediction tends to be more smooth if the input are smooth. We also found that when input features are of the same type, for example, we're using temperature. Temperature is the only variable we're using as the input. The digital twin error starts to be weakly depends on the number of features. More temperature inputs may not help to improve the performance of the diagnosis. However, when the input features are of different type, for example, we use temperature, pressure, and flow rates at the same time, we found out digital twin are more accurate and more robust against sensor noise. So the recommendation is if we are going to implement the digital twin for diagnosis with neural nets, we should start from simple and shallow structure that has fewer neurons and layers. And also, we should have only necessary and heterogeneous input feature feature for the diagnosis system. More feature does not necessarily give us better performance. And also we found out that scalability of diagnosis is a big challenge if we're using single neural nets to cover a wide accident scenario, because it really depends on the overlaps between training and application domain. Similarly, we also do a testing for prognosis. We also implement around 53 recurrent networks and 10 feed-forward networks, and all of them have acceptable training error. But the difference is we have sample some parameters from the where we sample the parameters with uncertainty ranges. And the summary of finding is that we found hyperparameters, the training parameters, like number of neurons, number of layers, they tend to have limited impact on the prognosis when we are using feed-forward networks. But when we're using recurrent networks, those hyperparameters start to have high impact. We also found that training a recurrent networks are more computationally expensive than training a feed-forward networks. And again, the overlaps between the training and the application domain have significant impact on the prognosis error. We also found out that the reference information, for example, the histories, physics, or reference variables, they have significant impact on the error of recurrent-based prognosis. And when we have more reference information, more knowledge, more history, and more physics injected, we're having more accurate predictions. So finally, the recommendation is for the prognosis digital twins, we should start from relatively deep and complex configuration that has more neurons and layers. And this is actually in contrast to the digital twin for diagnosis recommendations, where we suggest to have shallow and simple networks. And again, we suggest to have only necessary input for the prognosis. And also, but we should have as much reference information as possible, including history, variable, and the physics. So this is actually how we rank the importance of different input feature and reference information. This will be another topic. After the assessment for digital twin, we also do assessment for WAMAC system. And the assessment is done by doing sensitivity analysis for certain important parameters. There are 3 parameters we're sampling, actually 2. First is the ramping down ratio of the malfunction pump. And second is the time where WAMAC is making recommendations. And we found out that during a partial loss of flow accident, when pump 1 is ramping down 1% per second, which is also what we have in the training domain, WAMAC is able to make reasonable recommendation at different recommendation time. That means we have 0 false negative ratio with no fatal consequences. We have acceptable false positive ratio. And also that means we are successfully maintaining the peak field surrounding temperature below a safety limit all the time without either too conservatism or misjudgment. However, when we are testing our WAMAC system in different accident scenarios, the error starts to grow. For example, when we are testing WAMAC on a more severe loss of flow accident, where pump number 1 speed is ramping down more than 1% per second, the false negative ratio grows to 10%. And this is the case where the consequences can be fatal, because WAMAC thinks it is safe, but the consequence of proximeter tells it's not safe. For lighter scenario where we have pump 1 speed ramping down less than 1% per second, the false negative ratio is 0, but we have very high positive ratio, which is 60%. That means our recommendation tends to be more conservative. So a conclusion of this project is we have implemented a WAMAC and the corresponding digital twins. And the goal is to prevent the field temperature from reaching the safety limit during a partial loss of flow accident. And to be more specific, we're training a WAMAC system on an EBR2 plant simulator during the loss of flow accident. And the WAMAC is able to make a reasonable recommendation that is consistent with historical norm and for manual operations. Meanwhile, we do assessment for digital twin and WAMAC system to test the scalability of our digital twin and the WAMAC. we have make a list of social uncertainties for NAMAC system, diagnosis and prognosis digital twins. And we found out that the numerical results, we found out from the numerical results that the diagnosis and prognosis error are acceptable when we select the appropriate set of hyperparameters, issue space, and input feature. And how we select those features, it's another topic, and that is not covered today. And also we found that the digital and NAMAC error grows when testing scenario are outside the training scenario. So this is what we call the overlaps between the training domain and the application domain. So the next step is we are going to continue implementing advanced machine learning algorithms and integrate them into NAMAC. For example, the reasoning-based approach and also the reinforcement learning. We are also trying to conduct simulations with complex issue space and to have a much larger knowledge base. And meanwhile, we are trying to refine our development assessment process with the state-of-the-art artificial intelligence algorithms like meta learning. So this work is performed with the support of ALPHA-E program, and we have this is a collaborative effort from multiple participants from different departments, universities, and national labs. We also want to thank GOSIC to provide the lessons and support in constructing the EBR2 model. So that is all my presentation. Next, we will welcome my digital twin for any questions.
Thank you, Linyu. Question coming from the chat. Can you check that?
Yes. So it is from Anna. She is asking, should the operator know how the recommendation was given? Will NAMAC be able to explain reasons behind the recommendations? Yes, the operator should know how the recommendation is given. And as we see, sorry. As we see from the operational workflow, this operational workflow is transparent. So the operator knows what's the diagnosis output and what is the prognosis output, what is the predicted outcome, and why a NAMAC select these specific control actions based on the consequences and the preference structure. So we are setting this operational workflow transparent so that the operator know how the recommendations are given. Yeah, and yes, this will also include in the manual of the, if you're going to have this system, there will be a manual and that explaining how the recommendations are made. Okay. We have another question by William. You discussed the modeling EM pump for EBR2 as a test case. What should be considered when designing reactor component like EM pump for assisting semi-autonomous control? We are not, so first to be clear, we are not designing the reactor components. Those components are already there in the EBR2 system. But if you're talking about like how NAMAC could help in designing a reactor, yes, that is potentially that is what we think in NAMAC project is how we can use NAMAC to inform the risk profile of the reactor and to inform the design of reactors, like you said, the designing of reactor components. But for now, in our current case, we are using LAMAC mainly for operation that given with given components and given reactor designs. How we use LAMAC for vulnerability search for component design will be our next topic. Yeah, that is a very good question. Thank you. Okay. So another question by Kingsley. How do you make the distinction between causal variable and correlated variable for a given transient scenario in your neural networks? So with this is a tough question. So with the current artificial neural nets, which is a completely black box approach, it mainly represents correlation between variables, associations. So by only looking at the neural networks, artificial neural networks, we cannot tell whether it's causality, whether there's causation between the variables. So that's why we need some additional techniques to explain the artificial neural networks to help identify the causation between the input and output. This is one approach. It's called explainable AI. Another approach is saying that we should stop explaining AI. We should design an interpretable AI at the beginning. So for another approach, the AI are designed to be the neural networks or the artificial intelligence are designed to be inherently interpretable. So you can actually see what's the causation between variables by only looking at the neural networks. But this is a very immature aspect, and the people are still discussing that. So for now, I cannot give you a precise answer, but that's basically what I just said is how people how people think they should try to answer this question.
Any more questions for Linyu? Anytime you can contact Linyu in the department, and we welcome you to our group meeting anytime where we discuss these different technical aspects. Okay. So if no more questions, then we thank Linyu. Thank you, Linyu.
Thank you, President. Thank you everyone for listening.
Thank you, Lee. Bye.